So last week we have been talking about a coaxial line, which is the first kind of transmission line you have encountered within this course. We will still a little bit return back because we have not been touching power handling capability of that line. But first, before that, I will start to touch another topic. Just we had a transmission line or a wave that comes and encounters some impedance. This is more or less the same story for the case when we have a transmission line terminated with an impedance or when we have a plane wave approaching some interface between two different media. So there is a reflection coefficient and that is important to us. Let's call that reflection coefficient R, like last time, and just the important point, the reflection coefficient for the case of a plane wave is a ratio between the phasor of the wave reflected and the phasor of the incoming wave. So that's a complex number. Now for a transmission line, we do not have the need of specifying electric field strength. We can just integrate it over the end of the line and that produces a voltage. So we can also, for a line, put it like voltage reflected divided by voltage incoming. So we have with this two waves. There is an incoming wave that encounters the impedance at the end of the line and it might reflect back. It might reflect totally, which means that there is zero or infinite impedance, short or open end, or it might just reflect partially. Just to keep in mind that the reflection coefficient R is given by let's call it loading impedance Z load minus Z0, which this is the impedance of the line, divided by Z0 plus Z load. So this coefficient becomes 0 only if Z load and Z0 is equivalent, and in other cases there is a reflection. Well, first we should think now about what happens on the line when there is non-zero reflection at the end. That's an important question. So we originally had a wave traveling along that line. And that wave, for example, for voltage, could be expressed like voltage as a function of the distance z is some voltage 0, that is at the origin, times e raised to minus j k z. Well, those both are phasors, of course. So we have a wave traveling along the line, and we can decompose that into just phase change along the line and the shift or the decrease of magnitude, and that is then the equation for the phasor of the wave traveling along a transmission line. But now we have not only this wave. Remember, when we have been solving wave equation, we said, well, okay, there are two solutions. In fact, the wave can travel in both directions. So there might be another wave. Remember, it's some 5 lectures or 4 lectures ago, which would be some other phasor, let's call it V voltage of the reflected wave, and that is only different by having plus j, k, z in the exponent. So this sign determines whether that wave travels along the line in the direction of the xz or against the xz. And now we have this possibility, and this is a general solution. Those two waves could travel along that line, but this is not the case of a reflection at the end, or it is the case, but we can tell more. In fact, one of those two voltages can be selected as unknown, and the other one is given by the reflection. So if we know the terminating impedance and the impedance of the line, then we have a little bit different situation. We know that the reflected phasor could be expressed as the incoming times reflection coefficient. Well, this is especially true when we place the zero of the xz just at this terminating plane. So now we have established V reflected as a function of V incoming, and we can rewrite the equation. So we now have along that line voltage that is, and now we have V0 plus V0R, so we could now write it like, that's voltage 0 times 1 plus R So let's do it in another way. So this is the equation for the wave on a transmission line. Before we go on with this expression, let us think it over a little bit. Just imagine that we have a perfect reflection at the end. For example, that we have the loading impedance infinitely small, so there is a short at the end. So we will have a wave running back with the same magnitude. And in order to satisfy boundary condition at a short, it must be at this location perfectly antiphase, so that the wave reflects antiphase, and in the place of the impedance of the short, it cancels the incoming wave. So we now would be able to plot a dependence of the voltage on the line. At some point we have the short, so this is Z. At some point we have the short, and we know that there must be zero voltage. Now, if we go back, we have two waves. One is propagating that wave, the other is propagating that wave. What would be the phase difference between those two phasors, voltage O, VO and VR? Well, here it's perfectly antiphase, but the wave propagating there increases its phase in this direction at any time, the wave propagating back decreases it. So it happens that after just 1/2 of a wavelength, we have one voltage with this direction, the incoming wave, we have the other voltage, the reflected wave, and now those two waves as to phase along moving change, and finally they stand again antiphase, just 1/2 wavelength from the original short. So if we move again, just in the middle they are in phase, and now they again get the opposite phase. So what must happen is that we have the sum of those two phasors would look like this. And this repeats, of course, each half wavelength. So we would have a maximum 1/4 wavelength from the short when those two waves going there and back would be in phase and they add algebraically. Now we will have a set of locations at which those two waves would be antiphase. First the end, then half wavelength from that, and it repeats each half wavelength. And at those locations, those two antiphase waves would cancel each other. And this something is called a standing wave. A standing wave. Now, this is not very useful if you have a transmission line and you would put there a thing like this. You would encounter that there is no real propagating power. If you average the propagating power over a long time or over one period, you will get 0. Why? Well, just remember, we have had the reflection of magnetic field which was in phase. So the magnetic field would turn into this shape. And we will have two waves, one going there, one going back, and each of them carries the same average power over the line. So the wave carries the power there, it reflects and carries the power back, the same power. So we have no power in the terminating impedance. If this was the case of a power line from a power station, we would be transmitting huge power but consuming nothing in the load. This is not very helpful. So the standing wave, this is a perfect standing wave, which means that the reflection is 1, and we consider a lossless transmission line. Now this is a standing wave. Now let us get back to the equation. We can now rewrite it a little bit, and we could do that, for example, like this. So we will have the voltage as a function of Z. Still, remember we have a hat here, so it's a phasor. And this voltage would be expressed in two terms for a general reflection coefficient R, which could range from -1 to +1, and from -j to +j. It's a complex number. So now we have, let's say, two parts which I would describe in a few whiles. The first one is, of course, proportional to the incoming wave. So V0, that's the incoming wave. And now we have got a simple term, which is 1 minus R which is the reflection coefficient. It would be better to express that, I mean, the magnitude of R, not the phasor of R. And now we've got there a cosine of sorry, this is the real part, not just the phasor. So we have now the first part of the equation, and now this is not the whole. In the case that R is not 0, there would be another component which is now a little bit more complicated, and that is 2R B0 cosine and that is more or less the result. I have just used a simplification which stated that the phasor has a 0 phase at 0 coordinate. Not important, in fact, in reality. So we have two terms now for the voltage on the line. Now let us observe them a little bit. So we have one term which, in the case of 0 reflection, becomes voltage times cosine omega t. Sorry, minus, there is a mistake. So we have the first term that, in fact, in 0 reflection at the end, would give us a propagating wave. This is a standard equation for a phasor of a wave, for a voltage of a sine wave or cosine wave propagating over a line. Now there is an additional term. So this is let's call it a standard traveling wave. Let's call it traveling. And in addition to that, we have another term which is standing. So if the coefficient of reflection would be in magnitude unity, then we would not have this term, and we will only have a standing wave, like here. If the coefficient R would be 0, then we would have only a traveling wave and no standing wave. And what happens in between of that is that we have something between a standing and traveling wave, which looks, let's say, like this. So we would have again this graph with the z-axis. We have got the voltage over here, and the standing wave pattern would now be something like so. If we would have, for example, a probe, a voltmeter, connected just on the line, or a voltmeter with a rectifier, and we would move it on the line in the case where Z0 would not be Z load, but Z load would not be infinite or nor zero, we would get different readings of voltage on that voltmeter. And to have that somehow quantified, we would possibly introduce a new variable or a new quantity. which is called standing wave ratio. And the standing wave ratio is defined by two values. The minimum, which I would express by small m, and the maximum, which I would express as large M. Now again, how this has happened? Well, we have two waves. One is propagating in that direction, the other is propagating backwards. And at some places, those two waves get in phase, and therefore they add algebraically. At some places, those two waves get antiphase, and therefore they subtract one from each other. And the result is a standing wave ratio, which is given by the maximum divided by minimum. So we can see that in the case of zero reflection at the end of the line, the maximum and minimum would be identical, because only this part of the equation would exist, and therefore the standing wave ratio at best could reach the value of 1. In other cases, when we have some reflection at the end, the standing wave ratio gets larger than 1, and that might be a problem. Now, technically, why this is a problem? Well, first, you have some power that you transfer from the generator to the load, but it never gets into the load, it reflects back. So for example, if you have an antenna instead of a generator, and a transistor in the first amplifier, or in the first stage of the amplifier, if you do not have good impedance conditions, the wave travels from the antenna to the transistor, but it does not get in the transistor, so it's not amplified, it just reflects from the input of the transistor and returns back to the antenna and gets radiated somewhere. So this is the first problem. The second problem, let's consider a power transmission. In that case, you transmit the power there and back, and your line has to handle both powers. So if you are reaching the limit of power handling capability of a line, you get to a problem, because you might overcome or overshot it and get a destruction of the line, or just increased losses. For example, if you have a coaxial cable and you just slightly increase the maximum power that you can transmit, then there would be a discharge. So for slight increases, it would only increase the losses, because the excess power would turn into heat. But if you have really exceeded the maximum power handling capability, this discharge would generate so much heat that it would destroy the cable. And to have it quantified a little bit, let us now study the power handling capability of a coaxial cable in the case of a perfect termination, or in the second case of other termination, or a very bad termination, for example. But before we do that, we have been talking for some time, and I wait your questions. So if there are no questions, we will start examining the power handling capability of a coaxial cable. And we will soon get also to standing waves back. Now, in fact, there are at least two ways you can destroy a coaxial cable by the power that you submit through it to the load. The first destruction would be high level of current in the conductors that would cause heat and melting of the conductors. But technically this is not at high frequencies very much the case. So we have the other way of destruction, and that is by exceeding the maximum electric strength within the dielectrics of the coaxial cable. Now we should possibly look at the cable a little bit. So we have a cable which has a small conductor inside with the radius of A, and we have the other one which has the radius of B. And now if we draw the electric field strength, I will just draw the cross section. So we have the cable, and now the electric field strength looks like rays coming out of the, let's say, coming out of the inner conductor. And as you can see, the field is not homogeneous. In fact, we know that the electric field strength E is given by the linear density of charge sitting on the inner conductor divided by 2 pi epsilon r, where epsilon is the permittivity of the dielectrics, r is the distance from the center of the conductor. So this is the r. And now we can say that, okay, the field strength is inversely proportional to the radius. The biggest value of the field strength would inevitably be at the lowest radius, so it will be at the surface of the inner conductor. Now if we have there air, the maximum field strength that the air withstands would be 3 megavolts per meter. And this holds only for air in good condition. I mean, there is no water in it. So this is the maximum field strength that could be put there. So first, what is the power handling capability of a cable at DC? Let us first examine a cable that would deliver the power into a matched load. Let's say we have a 50 ohm coaxial cable. Delivering into a 50 ohm load. So that's an important point. So first, let us find the maximum or the breakdown voltage for a coaxial cable. Well, the voltage is given by the charge on the inner conductor, and so we could possibly do this by first finding the voltage between those two conductors, integrating the electric field strength. So the voltage between the inner and outer conductor voltage would be an integral from A to B, and we will integrate electric strength along a certain path. Well, we could choose any path, but a wise solution would be to integrate just along the radius. That would be most easy. So we have the E dr. Well, we could possibly first use it this way, but anyway, this is then by introducing the equation for E, this becomes tau over 2 pi epsilon r dr. because those two vectors are collinear, I have omitted the scalar product and vector notation. Now this, and this is a constant, and we are left with an integral from 1 over r dr, which is a logarithm, natural logarithm of r, and therefore we could easily write the result like the charge density over 2 pi epsilon logarithm of a to b. So this is the voltage which is here. Now this is generally the voltage for some given charge density. We have not established the charge density for the case of maximum field at the surface of the inner conductor. So now we would have to find out this charge density that is critical. And as we know that the electric field strength again is given by this charge density, that unknown one, over 2 pi epsilon r. And we know that the discharge first occurs at the surface of the inner conductor. We could put this equation a little bit more specific. So this is the maximum field strength, and it happens at the surface of the inner conductor. So we substitute A instead of R. And now we can establish tau. It is equivalent to maximum field strength times 2 pi epsilon. A. Now we can get this charge density and put it here into this equation, because those two values are relevant. And if we do that, we can have a new equation. So the voltage, the maximum or breakdown voltage between those conductors of the coaxial line are established by an equation which is maximum field strength times 2 pi epsilon A divided by 2 pi epsilon times the logarithm of the ratio A to B. Is the green color visible?
Yes.
Thank you. So now we can just cancel some terms here. I will do it by a black pencil, so the epsilon is not relevant or important anymore. We can cancel 2 pi. And we have the equation for the maximum voltage that could happen anywhere on the coaxial line unless it breaks. And it is given by this equation. So it is the bigger is the inner conductor, and it's bigger. It depends on the maximum or breakdown voltage of the dielectrics. Now this needs a short note. You may easily insert a better dielectrics which handles more power, but then you must be very sure that there is no small air layer at the inner conductor. If the dielectrics fits absolutely to the inner conductor, that's not a problem, but when there is a bubble of air, it would break, generate heat, destroy the dielectrics, and the cable would be break down. So anyway, this is an important equation, and mostly you should stick to the maximum field strength available in the air. Okay, so we have the maximum voltage on the line. And now let's have a question. So first we have a 50 ohm transmission line, and we deliver a power to a 50 ohm load. And let's do that at DC. So we have first a coaxial cable. Let's say we have a longer inner conductor, even here, so we connect the source between the inner and outer conductor, and over here we connect just the load. And it's 50 ohm. So if we deliver at DC from a 50 ohm, from the source to the load through a 50 ohm cable, our maximum delivered power would be voltage, maximum voltage, squared and divided by the impedance. So the power DC would be the maximum voltage squared and divided by the load impedance. Now just imagine that we switch from DC to 50 Hertz. 50 Hertz is nice because you would possibly never use a cable that is comparable to a wavelength, so that you would not have to care on any reflections and standing wave ratio. Just now we have an alternating current and the voltage copies the shape of a cosine. So we would have to think about, not about instant value, the maximum instant value of power delivered to the load would be again this number, but we have to consider time average of the power over one period, which is called